All right, so in my earlier video lesson, we have now come to a thorough and clear enough understanding of what a function is. And in that lesson, I have covered how we can have the basic operations with a function is, including function notations and all that. And so hopefully anyone, after getting out of that video lesson, already had a clear understanding of what to do with a function and what a function does for you. Okay, but now we're still looking at the function. We're still learning about function. But it's now time in this video lesson to advance our understanding about functions. So we're still talking about functions. We're still going to pull out some more details about function. But these details I'm pointing out in this particular lesson here, in this video lesson here, are going to be more advanced details. Okay, more advanced understanding of a function. Okay. And so bring back as much understanding from that lecture, from that video lesson that I've had about the introduction to the function or how we operate with that function. Bring back as much of those into the particular lesson so that the progress is going to be as smoothly as possible. Okay. So now, at the end of that earlier lesson where we talked about what a function is, I added up with the function representation as a table. So we were able to represent the input and the output values of a function in a table. Okay, and so now let me bring up a table. So throughout the entire lesson there, when I was introducing about functions, and so now usually when we already knew our function. So this is important. When we already knew our function and use a table to represent our function, then anyone reading the function will have a clear indication where the input is, where an input the variable is, and where an output variable is. And so let's say when anyone viewing this table I'm about to sketch right here on the table, on the board here, we're pretending that we already knew this is a function. This was a function, and we knew where the output is and where the input is. So I'm going to call the x column here is the input variable, and the y column here is the output variable. Okay, so, and then let's say I'm going to sketch down a few values that came out from my own creativity right here. That's how about -1, 0, and 2. Okay, so we don't need to have a lengthy table. Okay, just a table like that. And so we already knew that. So if this was a function and we had the y values here being the output, so let's say -9, -4, and 0. So when a table given to any one of us, and when we're reading this table, and when it was already clearly indicated that, hey, there's an input here and there's an output here, okay, then we know that, hey, the table itself has already been a rule. Okay, this table is just representing that rule. We may or we may know a formula for that rule. We may or we may not know the actual written down rule for that, but the table itself already represented that rule. And then the rule here specifically indicate that the input is here. We take input -1 and determine that the output is -9. Whatever that rule was, we may know, we may not know. That's not important. Okay. This rule from this table says we take input 0, put to output -4, and then we take input 2 and put it out to output +6. Okay, so like I said, so this table, when it's presented to you, it's meant that there has already been a rule, and it has already been decided. It has already been decided that there was a rule, and we further knew that this rule. It's also decided for us that this rule has whoever among the two variables here being the input, and this is the output. Okay, so there's the rule, there's an input clearly indicated, and there's an output. Okay, and that was the idea that we're summarizing from using tables as a representation of a function, meaning you're receiving a table that from someone who already defined a function, okay, or we're coming up with or if you are the one that working with a function and coming up with table, then this table is is sort of like the last step after you already had your function and successfully put the values in the table, where you have a clear indication of where the input and where the output is. Okay, so that's easy. So that was easy. We had the function, we know what that rule is, or sometimes we don't know, but somebody told us how the table worked. So the idea, all that is now the table we have been seeing, those tables we have seen in the earlier video lessons are all tables where it's already been prepared and indicated for us where the input is and where the output is specifically and clearly. Okay, and then once with those tables representing a function that we already knew it's a function, then here in this case right here, we're saying that y as a function of x, and we've learned that in the earlier lesson as well, this way of saying, okay, y as a function of x, because y is the output and x is the input. Okay, but so now I just need to bring up an understanding as following. Now things won't always go as easy, because and the reason I was saying in the beginning that things can become a little more advanced here, and we need to, and this lesson here is specifically aimed at students who are in pre-calculus level, where your mathematical mind has become a lot more mature than those who are just in elementary algebra. Okay, but so I also mentioned earlier in earlier lessons when we were still introducing about functions, then so now I mentioned clearly in my earlier lessons that naming the input doesn't always have to be x. Take my words on that. And also naming the variable for the output doesn't always have to be y. Okay? That's why just now I erased the line that the indication that, hey, this is the input and this is the output. I erased that. So now roll yourself back to that position where you just simply received a table. Somebody gave it to you. Hey, here you go. Here's a table. There's the x value. There's the x values. But there's the x variable with a few values here. There's a y variable being listing a few values here. So these values, the -1, the 0, the 2 are the values for the x variable. The -9, the -4, the 6 on this column is for the y value. But this table is presented to you simply just that. Notice there's no indication who the input is and who's the output is. There's no, because now the point is any one of these two variables can be the input. Okay? The rule isn't here. The rule is in the table itself. So now my point I would like to say now is that when you're simply just given a table without any clear indication, and someone just simply give you a table without telling you if it's a function or not, it's just simply a table given to you, okay? Then really this table here, each one of the two variables here has its own right to be the input. So earlier I was treating this x as the input, but now the same table here, we can also treat the y variable as the input and the x variable as the output as well. So what's the rule? The rule is right here again. I'm not saying that it's this. I'm not saying that it's the same rule. Okay, the same table, -1, 0, and 2, -9, -4, and 6. If we treat this variable x as the input and the variable y as the output, there was a rule. Knowing it or not, that's not important, but there was a rule. And now if we reverse the other way around, we think about the other way around, if we're treating the y variable, and like I said, because naming the input doesn't always have to be x, doesn't always have to be y. It can be a t, it can be a z, or whatever. But so now if we seeing just simply a table on its own truth, on its own very fundamental truth, then any of the two variables listed here can be the input. So in this case right here, if I'm saying that the y variable being the input, then it's a different rule. Same table, but it's a different rule pointing out how y determines the output x equals -1 correspondingly, and how the input -4 for y determines the output 0 correspondingly. So this was a rule here. Okay, and the input was the x and the output was the y. Okay, but now same here, it's a different rule. So now I have to mention it's a different rule. Okay, but it can still take an input, and the input this time reverse the role. The y is the input, and the x is the output. It's not going to be the same rule, but in the end, I still see there's a rule to decide an output for each input. There's a rule to decide an output for each input. Okay, and that's the advanced understanding that I'm about to lead anybody learning in this video lesson into right there. Because a lot of times functions, a lot of time tables are given at us. Okay, now we need to decide. There's the kind of problem right out there. There's a kind of challenges out there. Where simply a table is given to you, where I just now pointed out any one of the two variables listed in your table can be regarded as the input, and the other one is the output. Okay, see, there's a rule, there's an input, there's an output, there's a rule, same table, but we can see the rule here is going the opposite way, taking the x column as the input and taking the y column as the output. So there's a rule, there's an input, and there's an output. Okay, there's a rule, there's an input, there's an output. But now, which one of these rules can be a function? Because not so fast, just simply because there's a rule to decide an output for each input. There's a rule to decide an output for each input. Doesn't always mean it's a function. Okay, and so now we have to dive into that kind of problem right there. And so now allow me to bring up our first example in this video lesson right here to demonstrate the idea right there. Okay. All right, so now after erasing the board and keep it clear, now let's look at our example 1 in this lecture, in this lesson right here. So I'm just simply given a table, and again, I'm asking anybody to not to worry if it's a function, because that's the point. We just simply have a table given. I don't want you to think of that as a function. The table itself is not always a function, it's just a table. Say table is a list. Okay, so now let me give the following table. So given the table as following. All right, so here's our table. Let's look at and this time I purposely want anybody to break away from that habit to always tie yourself down to x being the input and y being the output. So I purposely use the two variables that are completely aside from x and y. There's t and v. All right, so now we really are stepping away from the tradition. But it could be a good thing so that we can open our understanding into a much broader point of view right there. Okay, so there's a t variable, there's a v variable. I'm not saying who's the input and who's the output. Okay, I'm not saying who's the input, and I'm not saying who's the input and who's the output. So simply it's just a table that's listing the values of two variables. Okay, so t has a few values listed here, 1, 3, and 0. Organizing t or not, that doesn't matter. But so t is made correspondent. T is having a corresponding value in a v column. There's a 2, there's a 7, there's a 1. Okay, it's a table. It's just a table. So now, just like how alongside with what I have explained right before we start stepping into this example, then between or among the two variables here, any one of these can be the input, and the other one, of course, is going to be the output. So you can make choice to make one being the input and the other one being the output. Okay, and so in that way, how about I'm going to start out with part A. So allow me to switch over to the other board. So from that table that I hope you have taken notes. Okay, let's look at question A right here. Let's decide, okay, decide whether the table, okay, whether that table given earlier on the other board represents V as a function of t. All right. We want to decide, and let me underline this with red ink, or maybe I can even erase and change it out with red ink right here. I want to decide, I want to determine whether V can be regarded as a function of t. Okay, V as a function of t. All right, so I will eventually, or sooner or later, switch back to my earlier board right there, where I showed that table right there. So make sure, I mean, as you follow along with this lesson, take it as formally as you're sitting in a class and learning it from me. So take note as much as possible. So now I'm going to switch the view back to the table. Okay, but now before I leave, again, the phrase here is familiar, and I brought up this phrase right here back in that earlier video lecture, where I introduced the function and function notations. Okay, I mentioned this kind of phrase right here, quite common phrase right there. Okay, so this phrase right here wants us, according to this requirements, we want to see V as a function. It's a variable, and t is also a variable, but V as a function, and then t as being the variable. And so also I brought in, and anyone up to this point has already been introduced to the term dependence and independent. So the two variables here, this one here, intended to be, we want to decide if this can be an independent, okay, variable, and whether this can be the dependence variable. Okay, dependent and independent, but more importantly, can that be a function? All right, and so now, having enough highlights with the information here that we kind of break it down throughout the wording right here, let me switch back to the table. All right, so in this table, in the way it is, we want to decide whether V can be regarded as a function of t. Then that means, tentatively, we want to see V as the output, and we want to see t as the input. Okay, we want to see V as the output, and we want to see t as the input. All right, and so now, combined with what I explained earlier, before we stepped into this example, then yes, a table is just a table. So any one of the two variables here can be the input. So let it be. The problem wanted us to see V as the output, and the problem want us to see t as the input. That's completely okay, no problem, no need to decide, because any one of these can be the input, and the other one is, of course, the output. Okay, so the wording of the problem early on the other board led us into seeing that the problem say, hey, let's purposely see t as the input and see V as the output, and that's why I wrote that in red ink on the other side of the board with that table. But now the important thing is, yes, so now we had input, we have output. Okay? Can that rule, and not to mention, and I forgot to mention just now, anytime that we decide who the input is and who the output is, okay, there has to be a rule somehow. Knowing it or not too important. See, once we have decided this is the input and this is the output, we just simply decide out of random, but there has to be a rule somehow. Is that an equation? What's the equation? What's the formula that decide that rule? We don't need to know that. Just say, or you can think about this table itself already represented a rule. Doesn't have to be a common rule or anything like that. Okay, and you have seen this kind of example back in your in that video lesson I delivered earlier when I was introducing function and function notation. Okay, so this table already represents a rule itself, some rule that we know it explicitly, specifically or not, that's not important. But now, so let me quickly make that list. Yes, it was a rule, because once we decided who's the input and who's the output, then there must be a rule. and then we want the inputs, in this case we want the input to be t, and we want the outputs to be v. Okay, so I thought it's a function, but not so fast. That's the part where we have to decide. Just simply because it has a rule. Because apparently there has to be a rule somehow that brings this inputs to land on that output. The rule has to, whatever that rule says, it brings the 3 and land that into an output 7. And it brings this input 0 and land that into the input and the output 1 right here. So there's always rule that takes an input and land that into an output. But will that be a function? That's the part making it a challenge right there, and that's the part where we are learning with reasoning to decide, can that be a function? Can this rule together with this input and output be a function? Okay, and so now at this point we have to roll back to that definition of a function that I delivered in that earlier lesson, and that's why this particular video lecture here is usually like the very next one after you have learned about how I introduced a function and function notation like that. But just simply having a rule that takes an input and land that into an output is not enough. Okay, the definition of a function says a function is a rule that determines an output. But you have to remind that determines one and exactly one output for each input. One and exactly one output, or I may have said it a little bit incorrectly, but exactly one and only one output for each input. Okay, a function is a rule, okay, that determines exactly one and only one output for each input. That's the part decide whether this table can be a function or not. So only having 3 requirements here is not enough. Remember that when I talked about what's common, that made up a function. There are actually 4 requirements. We have to have a rule. That's the most important thing. But and of course the rule takes an input into an output. But on top of that, it needs to be one input going into exactly one output only. One input going into exactly one output only. That's the critical part. And so that's the part we need to check right here. So let's look at that. If this is now the input, well, according right here in this table, I see it's outputted into a 2. Does this same input goes into any other different values? On this same input, does it generate any other value? Nope. 2 is the only output it has. So it works on that one. But we have 3 different we have 3 different inputs for this table. So let's look at the other one. 3 goes into 7. Right here, our eyes can see it. Okay, but now you have to check, does 3 determine another output? Does 3 land into another output? Nope, this is the only one. So again, we're looking at exactly and only one output for that particular input. And that's what I'm talking about right there. A function is a rule that determines exactly one output for each given input. Okay, and so in that way we have one more input to check right here. 0, does 0, well, right here in this table, 0 goes into 1. Well, it looks like that 1, but it's just a number. But now this 1 right here is listed as one value among the output values. Okay, but at least the way how I see it is 0 as the input right now goes only to 1. Okay, or there's only 1 being the only output for 0. 0 doesn't go to 7 at the same time. 0 doesn't go to 2 at the same time. So now I can say yes. For each input, there's exactly one and only one output. See, for each input, there's exactly one and only one output. Okay, and so now you can say. So the reasoning here, the observation here says, and here it's just because I'm showing the steps, so I'm just showing that reasoning here. But if you are actually doing an assignment with this, you don't need to write down this reasoning. All you do is just observe the table, and I already show you that table. Okay, so for each input, okay, there was, because we saw that earlier, there was exactly one output. All right, so this is the part where it really met that final requirement for being a function. We passed that. We passed this checking requirements for, based on the definition of what a function is. So now deciding whether this table, this same table we've had, can be deciding whether this table represents v as a function of t. Now you're saying that, okay, you can just simply say yes, because is that a function of, yes, v is a function, okay, of t. V is a function of t. Okay? And then simply in a notation setting, you can say that v equals, you can give a function's name, f of t. V is a function of t. Okay, that's in equation notation. This is in word right here. That's how we decide, and ultimately decide whether it is a function of t. That's yes, we've had that. Okay, and so let's not rush to get out of this example. Same table. Now I'm going to have to erase out all of these extra notes right here. But I want to retain the exact same table because we're still in example 1. All right. And now I'm going to move over to the other board. And I'm going to write down the next question. And we are still doing the exact same thing. But now I call that part B. I want to decide the same table. I want to decide whether the table represents t as a function of v. All right, so how about instead of writing that in the traditional black ink, why don't we just write that as, all right, so can t be regarded as a function of v? Okay? Or formally speaking, the wording of the question says, decide whether the table, that table you've seen in the other side of my board right there, that same table, we didn't go anywhere aside away from that yet. We want to see if that table represents t being the inner function. So this time the two variables switch roles. Okay, can t be a function of v right there? Does the table represent t as a function of v? So now we have had some experience from the earlier problem. That means we want the t here in this time. This time we want the t to be the independent. I mean, we want t to be the dependent variable. The dependent one, and v here is to be the independent one. All right, that's the idea right there. Or another way of saying, now back on my other table, then these two switch roles. Okay, now I have to erase them. Okay, see, I should have erased them right after I finish part A. But now in part B, we want t to be the outputs. We want this t to be the outputs. And we want v here to be the inputs. And that's the idea, because like I said earlier, before we stepped into this example, a table is just a table. Any one of the two variables here, any one among t and v can be the inputs. So this time we purposely want, we wanted v to be the inputs and t being the output. So this is the same table, but it's now this same table represents a different rule being represented in here. We know that rule or not, I mean, we see that rule or don't see that rule, that's not important. Seeing that rule as an expression, seeing that rule, what's the expression, what's the formula that take 2 into 1, that's not important. All right? But the point now is that if we want the v variable here to be the inputs and the t variable to be the outputs, there must have been some rule. Okay, so the rule exists here again. It's not the same rule as the earlier one in part A. But then that rule, yes, it takes the inputs. In this time, the input it takes is the V, and it lands each input into an output that's among an output's value that we generally regard as the t variable. Okay, so we got a rule, we got an input, we got an output. And that's easy. That's the easy part. The harder part, the more challenging part is, can this rule, taking every input V and outputting that into a t correspondingly, can that rule be a function? Can that rule be a function as stated here? That's the part, and that's why I've been highlighting, underlining that term as a function, okay, throughout the two parts about the two problems of our example 1 here. Okay, and so now we want to decide whether that rule taking t as taking V as the independent input, and then taking that into determine the output being the dependent variable here. Can that rule be a function? Okay, so now the only way to answer that, does it pass the fourth requirement? Does each input gets taken into one and exactly one output? Does this input gets taken into one and exactly one output? That's the question we have to check for ourselves. And so let's check. This time the arrow goes the opposite way. If this is the input, 2, well, for now right here in the table I see 2 is taken and 2 lands right into that output 1. So 2 is the input, it lands into that output 1. Is this the only one and exactly just the only one in this table? At least in this table? Yes, it is. Okay. Then we move on to the next one. 7 is the input. It gets taken into an output. Okay. See, the rule takes an input and bring that into an output and land that into an output. That's why you start hearing me saying the word taken. Okay. An input is taken and put right into the output right there. And how does it do that? The rule somehow does that. Okay. But in the end, ultimately, for this input, is it taken only into one output? Yes, only one output is assigned for that input. See, it doesn't go like this. All right, and then this output rate, this input right here being a 1, is it only taken to output 0? Yes, output 0 is the only output for that input. The only output for that input. Okay, and so now, yes, we want to decide if this rule right here can be a function or not. Okay, because any rule is just a rule. A rule, basically, how we bring an input to an output, it's a rule. So that's why anytime there's a rule, you bring an input to an output. But now, can that rule be a function? That's what matters right there. And so now, according to the arguments, to the demonstration I have just done, again, that same reasoning. We notice, we observe that the observation here is, after the observation here, we see that for each input, okay, for each input, okay, I found that there was exactly one and only one output. That was the main observation for each input that we found, that we observed. And this is the reason why it leads to, now we can say, yes, again, the same table. We're looking at the rule in the reverse way. The same table, but yes, it's a function, okay? T is a function of V. That's how it is. That's one way of saying that. And now I can, in equation notation, T is the dependence variable. So that's, now I kept saying it's not the same rule. So that's why I don't name that F of V. I'm naming it G of V, because we're still in the same example here. I want to use different names because they are different functions, different rules. So G of V here. The function G, take input V and land those inputs into an output T, an output that we call the variable T. Okay, and so that example here just showed us that kind of problem where that challenge came when a lot of times we have a table simply just a table. No one told us anything about is a table a function or not. And so we want to decide that, and so now that's how it was done in example 1. But now to enhance your understanding and to enforce the idea that each input, because that's a very critical requirement for being a function, because having a rule can be anywhere, okay? A rule is just simply a rule, a rule that determines how we take an input into an output. But now what makes it a function is that for each input there has to be exactly one and only one output. Okay, so now take that requirements in mind right there. And so now I'm going to call that example 2. And the good news is pretty much the exact same kind. I'm just simply going to give a different table. And so I don't have to erase too much and rewrite too much. Okay, I can just simply erase out this table and retain the rest of the wording. All right, so here we go. Example 2, we're given a different table as the following. Okay, so now with this table, this time let's call that, how about this is W and V right here. All right, 2 variables. Any one of them could be the input and the other one is, of course, the output, okay? 1, 2, 3, 4, 5, okay? And then the other variables here, I'm looking at 8, 6, 7, 8, 7, 6, 7, 8. Okay, those are the output values. I mean, those are the values for the V variable, and those are the values for the W variable. I shouldn't even say output or input, because any one of them can be the outputs, and the other one is, of course, the input. All right, so now with this table, now we're calling that example 2. Pretty much same exact idea. We have a table given, right? That's listing out values of 2 variables, and I purposely stay away from x and y because I believe that a lot of students have been stuck in that tradition that x is the input and y is the output. So if I brought in this is x and this is y, you're gonna stuck permanently with this is the output, and it's hard to get out of that habit once you set into that habit. So here I just call it W and V. Any one of these, that's the point. Any one of these can be the input, and the other one, of course, is the output. Okay. So now we're going to learn to decide carefully. All right. All right, so now here, part A of the example. And it's the exact same requirement. It's the exact same instruction of the problem right here. We want to decide whether the table represents V. And let me write that in red ink. Does the table represent V as a function of W? Okay. Decide whether the table represents V as a function of W. Okay, so now take as much of experience from example 1 we have done earlier into this as possible. So we want this to be the dependent variable, or in other words, we want this to be the output. Okay, and we want that other variable W to be the independence. Okay, so I want that to be the independence or the input. That's what it is. Okay, so if that's what we want, if that's what we want W to be the input and we want V to be the output. Well, let's head back to the table. Okay, so if we want this is to be the input and this is the output. Okay, and allow me to be a little bit improvised right here. I mean a little bit sketchy right here. In just mean input and out just mean output. Okay, so if we want that column here to be all the inputs, then once again there has to be a rule. Knowing what formula, what expression that is, what mathematical expression that brings this input to that output, we don't have to see that, we don't have to know that, It's not important. What I mean is knowing that rule or not, knowing what that rule exactly was, explicitly written out, that's not important. Okay, we just know that there's a rule already. There's a rule already that now takes the inputs to be the W variable and landing each input into an output being in a V variable. So there's a rule, okay, that takes an input into an output. So we know that, that's easy. Okay, what matters for us now is, can this be a function? All right, so just because we have a rule doesn't mean it's a function yet, right? So we have to look for the next requirement to see whether that our rule here satisfies that requirement. So what is that big requirement? Does each input get taken into one and exactly one output? So we have to check that. That's the part we have to check. This input, is it taken into exactly and only one and only one output? Well, 1 goes to 8. That's why I'm drawing this arrow. Does 1 goes to anywhere else? Nope. Or do you see anywhere else there's a 1 and then gets mapped into a different value? Nope. And I use that term mapped. That's some of the old-fashioned term right there. We take a value, bring that into an output, and that's called mapping. Okay, we map an input into an output. There's so many ways of saying it, but in the end, what I'm seeing is for this particular input being 1, it's only taken to 1 and only 1 output. Okay, let's check again for the other input. This input 2, is it right now in what I see in this table, it's taken to 7 as the output, but is it taken to anywhere else? No, that's all there is. That's all there is. Okay, that's all there is. And so we're good for that one. For this input, there is only 1 and exactly 1 output. Okay, and then for 3 as an input, now right here in the table I see 3 is taken to 6 as the output for the output. And is that the only output for 3? Yes, that's the only one. Okay, and then the same thing with 4 and the same thing with 5. Okay, so now as far as meeting the requirement for each input, there is only 1 and there's exactly 1 and only 1 output. Then this way right here, seeing the W as the input and seeing the other one is the output, that's satisfied, that meets that requirement right there. So now I'm going to go back and write down my final decision. All right, so the observations say, so according to the observation, I see that for each input, okay, again we notice there was exactly 1 and only 1 output. All right, so this requirement here is checked. And so, yes, now I can see that this table represents V as a function of W. Or I should have said V is a function, okay, of W. All right, and then that means in equation notation, V equals some function. Let's call that H of W. W is the input, so I'm using functional notation. And together I wrote down that equation notation, equation style notation. Okay, and so that's how we decide. But then let's wrap things up into part B right there. Pretty much the same instruction of the problem. So I'm going to erase this. All right, so now part B of the example. Same table. I want to decide whether the table represents W as a function of V. Okay, so just like that, we want W here to be the dependent one. Okay, and This is the output, of course. And we want V is playing in the role of the independent variable. Independent variable, and this is the input. Okay, and that means back at this table, I want these two variables switch roles. So allow me a minute here to erase out all of these hand sketch notes right here. All right. So I want, this time I want the output is here. We can want anything we want, okay? But what we want give us a function. All right, so we want whoever between the two here being the input and the other one being the output. We can always desire that. What matters, again, will what we want bring us into, or will what we want give us a function, okay? And this is now input. I want this is to be the input, and that's the output. All right, so yes, there's a rule again. Apparently there has to be a rule. We don't have to see specifically or explicitly what that rule, how that rule is written down. Or it's already written here in this table. It's already described in this table. Okay, with that rule, takes the inputs. This time the input is the V variable, and it takes each input value into an input, into an output that we call W. Okay, so now let's check again. Let's do the same checking. But see, 8 being the inputs. According to this rule, it's this rule represented by this table. The rule represented by this table takes 8 and map 8 into 1, or takes 8 and land into 1. Let 8 lands into 1. Okay? So 8 lands into 1. So this is the output. We see that there's one output for now, but let's search through. There's another 8. So 8, as far as value, it's one value. So one value for the input. One input. But all of a sudden we spotted 8 also goes to a different output. Okay? 8 same input value goes into 2 different outputs. Yeah. And when I was introducing what a function is, I said specifically clear that the idea about an input going to 2 outputs means just like this. If we use that same input value again, for some reason it runs into a different output. That's not good. Think about being a machine. If today, think about that vending machine I talked about in that earlier lesson where I introduced the idea of a function. So think about it. The vending machine today is for some people the vending machine takes $1, give you a soda can, but for somebody else the vending machine takes the exact same inputs, $1, but give that a water bottle. That's not a good thing. That's not a well-functioning machine. Okay? And so in this case right here, it's right there, 1 input but goes into 2 outputs. Okay? So immediately as soon as we spotted that, well, regardless of whatever happens here, well, that goes only to 1 output, that goes only to 1 output. And actually, I noticed the 7 here, the same 7, but goes to 2 outputs. So we spotted 2 values where each of them goes into 2 separate different outputs. That's not good. Okay, that's not good. And so once again, can this rule be a function? Okay, now I'm starting to yell out loud. Uh-oh, something's not right. Okay, uh-oh, something didn't look right here. Okay, all right, so now let's come to our final conclusion. You see, so 7, okay, is taken to 2 values. Okay, what are those? That was 2 and 4. So we already failed. I pointed out. I pinpoint that we failed that requirement for each input. This is an input, but there are 2 outputs for that input. Same thing that happened with 8. We spotted that with 8 first. So 8 is taken to two values, and I should have said two output values, okay? Two output values. Those are 1 and 5. That's not good. All right, and so in this case right here, back to the question, the ultimate goal we're looking at, we're trying to decide whether the same table can represent W as a function of V. It's a rule, it's still a rule, but this time the rule here, this rule fails to be a function. Okay, so nope, W is not, okay, a function of V. All right, and then as soon as we concluded that it fails to be a function, I don't even have to write W equals the function of V anymore, because it's already failed. All right, so that's what happened with these kind of problems. So a lot of time we have a table given, because in the end, remember, a table only represents the values of a function. So simply just having a table doesn't always mean it came out from a function yet. So in order to see clearly if it's a function or can be a function or not, we have to decide carefully, and that's how we do that here in this example. Okay, and then so there will be other challenges out there, where we have to decide. We're in a situation where we have to decide. The point now is that we have a rule. The table represents a rule. We have a rule. A lot of time, see, we have a rules, and after this problem right here, I'm going to bring everyone into a different kind of challenge where we see a rule again. A rule can always, there will always be a rule existing out there that brings an input into an output, that brings an input into an output. But can that rule be a function? Then that's where you have to slow down a little bit and decide carefully, because we need to meet the fourth requirement. Will each input get taken into exactly one and only one output? That's what matters right there. Okay? All right. All right, and so at this point, apparently speaking, it is what we're learning, that we need to decide whether a given rule is determined, or a given rule determines a function, can be decided as a function of one input, Okay, and so earlier in this lesson, we have already seen how we can decide whether a rule that's represented as a table can be regarded as a function in terms of the input variable. But now let me bring up a different situation. We're still deciding whether a given rule can be a function or not, but let's look at some other situation right there. So I recall that from an earlier lesson, from an earlier video lecture that I brought in, that was where I introduced the function and function notations again. And so I brought in the following equation. Okay, so let's look at y equals 5x minus 4. And I remember clearly that this was one of the example problems in that earlier video lecture right there, when I was introducing function and function notation. And so you can always go back to that video lecture and view this example. But so we know that this was a function, because I in that example there I mentioned that this was a function. The rule is here. Okay, and so we already knew, because right from the beginning of the problem, we were given that this was the rule, and so we decided that's the rule. That's a function f of x. We named the function f, and then the output is assigned to the variable y. Okay, and so I call this it's a function, but it's in equation notation. So it's just a way of writing it down. Equation notation. But then in the way how it is, then there's no need to argue about it. Y is if you see an equation like that, now then y is a function of x, clearly. Okay, y is a function of x, clearly. So I explained that there in that earlier lecture, that a lot of time we use an equation notation to write a function. But that's also where it brings us into some challenges right there. because now equation, a function, working with a function is not the only place where we use an equation to write a function. Okay? Working with a function is not the only place where we write down an equation. As a matter of fact, there are so many equations out there. Okay, so now this equation, I'm only briefly bringing it back to recall that when you're writing down a function, we do use equation notation, and that's where it leads into the kind of challenges for us. The kind of challenge for us that a lot of time we are given an equation, two variables just like this, and we need to decide who can be the function in terms of the other one. Okay, and so let me now bring up the following. All right, so what about 8 equals 10x minus 2y. 8 equals 10x minus 2y. Okay, it's an equation now. It was not a form, it's an equation, but it's not a function yet. How can it be a function? We don't know yet. It's just simply given an equation. Okay, and so simply just an equation itself. So I really need to emphasize from what I was saying earlier, the point now is that just because you have an equation doesn't mean it has to be a function. Okay, so the way how I see this equation, it has two variables involved. It has two variables involved here. Okay, and so now, just like how we were working with tables earlier, we had two variables back then. Okay, I purposely use the variables other than the x and y. So here I started out using x and y, but now I also need to emphasize any one of the two variables here, x or y, can be any one of these can be the input. And of course, once you have picked one to be the input, the other one can be the output. Okay, so here's how it works. And that's why, again, let's look at the table of values here. I'm just going to make a list. There's x, there's y. Let's for now look at, let's for now pick the input to be y. Okay, let's pick y as the input, and we want outputs to be the x. If that's so, like I said, this is what we picked randomly. So there has to be a rule to do this. Okay, so what rule is that? See, so if we picked, and remember, if we pick one to be the input, then that one is the independent one. So y is the independent one. So we can pick -9. Just out of nowhere, I picked -9, just out of selection, my own selection. So if we pick y equals -9, the whole point of an equation now is that what if we substitute this, because that's what an input is. We take this value, we substitute it into the equation. So we have 8 equals 10 times x minus 2 times -9. Okay, 10 times x minus 2 times -9. But so minus 2 times -9, that's a positive 18. And so here we can solve, wait a minute, we ended up with an equation that we can solve for the corresponding x value, because once we decided that, once we have picked y equals -9, then we can find the corresponding x value that satisfies the same equation. Okay, and so this equation here, I have 10x, right, equals, and that's positive 18, but subtract to the other side, it gives me a -10. Okay, and of course, anyone in this class, anyone viewing this video lecture is at the pre-calculus level, so allow me to skip some of the small detail steps here, and then now we're dividing both sides. So first I multiply that as a constant term and subtract that to the other side from both sides. That's how I ended up in the next step, minus 10 equals 10x. And then I'm dividing both sides by 10. That leaves me x equals -1. So this is what I call the output. So once I pick the input independently, I can find the outputs corresponding. I can find the corresponding output. So this is now output This is now input. I picked -9, I ended up with output being -1. What was the rule allowing us for that? The equation itself here is the rule. Because the rule says no matter how you picked y, the x have to come out accordingly to satisfy this equation. Okay, so the equation itself is the rule. This is the rule, and that rule governs, that rule helps us determine once we have picked a y value, an input value, how can we come out with the output. Okay, and so that's that, but that still I didn't say anything about the function. I didn't say anything about being a function. All I can say is we clearly see a rule this time. And then from that rule we can organize things in a table. So let's pick again. I can pick y equals -4. It's just another independent selection of mine right there. Okay? And so the rule is here. 8 equals 10 times x minus 2 times -4. Let's make it 10x plus 8. And I'm subtracting 8 from both sides, so I'm ending up with 0 equals 10x. Okay? 0 equals 10x. So that gives me, and as I said, anyone viewing this video lesson should be at the pre-calculus level. So allow me to skip some of the little detailed step in solving this equation right here for x. Because the point now is that we picked y independently, but we want to come out with, based on this rule, we want to come out with the x value correspondingly that satisfy this equation. So that's the way we solve for x value correspondingly. And this is where you need to master your skill solving an equation prior to entering any of these pre-calculus video lessons right here. Okay, and so dividing both sides by 10, I'm looking at x equals 0. So if we picked y equals -4 as the inputs, the only outputs that satisfy this rule, the only outputs, it has to go to 0. So the rule itself, again, this equation itself is the rule that determines for each input we come out with an output. Okay, and I can pick 6. Okay, I can pick 6. All right, and so again, what do I see? The rule takes in inputs, give out an output. Okay, so in this case, let's see if that rule will give us. Let's see what that rule will give us for an output here. So 8 equals 10x minus 2 times this times y. This time y is substituted by 6, positive 6. So minus 2 times 6 is -12. I'm going to add that to the other side. So that's making it, so there's 10x, but minus 12 here, add it to the other side together with the 8. I'm looking at 20. Okay, I'm looking at 20. And so now solving this equation for x, we know enough skill that we just divide both sides by 10. And that gives me 2. So x equals 2. So the output here correspondingly has to be 2. Okay, I've spent time enough with that. So the point is we have a rule. The equation itself is a rule. And that's why I said it earlier. Just because you're having a function and your function is written as an equation doesn't mean any equation can be a function, because any equation can be a rule. Any equation can be a rule. And so your function written as an equation is no exception. Your equation can be written as your function can be written as an equation, and it's already a rule. Okay, a rule that determines an input and output. Okay, but for a function it's being a little more explicit. But then now, something like this, can it be something like this? Can it be a function? Can this rule be a function? That's the next step we want to challenge ourselves right there. Okay, but then let me illustrate a little more. The same table right here. Well, there's already the rule, but what if we switch role? Okay, what if we switch role and we want the inputs this time to be the x, and we want the outputs to be the y? Again, still, this rule relates the two variable values here together. Okay. This time, what if we want this is to be the input and this is to be the output? Okay, it's still going to work. So I once again emphasize what I said earlier. Anytime you can have an equation or you can have a table, any one of the two variables can be the function. I mean, any one of the two variables can be the inputs. And once we have chosen the inputs, the other one will be the output. Okay, and your rule sometimes given as a table, sometimes it's here in an equation, and we use that to sketch a table for us to organize the values right here. Okay, so this time in this equation I chose x. I picked x randomly to be the input right here. So if x is -2, okay, in this equation it becomes 8 equals 10 times -2 substituted for x minus 2y. Okay, that's the rule. There's a rule. It relates the two variables together. Okay, and if we decided that, hey, we want x to be the inputs, how are we going to come out with the y outputs here? Okay, so that gives me -20, and then I'm going to add that -20 to the other side, so I'm looking at positive 28, right, and equals minus 2y. Okay, positive 28 minus 2y, and so I'm dividing both sides by -2. I'm ending up with y equals -14. Okay, so -14, that's the y. This is now the output, that's the input. That's why if we decide these two variables to switch role right there, then we have to always start out with the independent inputs, and then we calculate the outputs accordingly. Okay. Similarly, let's come up with x equals positive 1. Okay. And so 8 equals 10 times positive 1 minus 2y. 10 times positive 1 is a positive 10. I'm going to subtract that to the other side, and that gives me a minus 2 equal, okay, minus 2 equals minus 2y. And so now solving this for y value, because we want to come up with what's the output value for y. Okay, so dividing both sides by -2, I'm looking at y equals positive 1. Okay, so y is also a 1. I mean, it happens to be the same looking number, but it's one output. Okay, and let's look again. Now let's say I'm picking 3 for the x input. All right, so now I'm looking at 8 equals 10 times 3, okay, minus 2y, okay. So that's making it a positive 30 right here. I'm subtracting that to the other side, okay. So that gives me minus 22, okay, equals negative 2y. I'm dividing both sides right here by -2. That gives me y equals a positive 11. Okay, positive 11. All right, and so we have been having, so I just want to demonstrate again, similar to having a table. So now you have instead of having a table, you have an equation that connects, that relates two variables, x and y, or v and t, or v and w, or whatsoever, two variables involved in your equation. Then you can pick any of these two variables to be in the role of the input, and the other one can somehow be solved for as an output. Okay? All right, but will that equation decide a function? Now hold it, don't decide rashly. We need to head into a formal example where I show you, because all we see here is the rule. It takes an input to an output, that's all there is. But now we want to know, can that rule be a function or not? That's what we need to decide. Okay, all right, so now let's head into a formal example. So things are going to start going a little abstract here, okay? But believe me, follow with my instruction here step by step, and you will get a good hang of it. Okay, so now let me call that example 3. All right, so in this example, we have an equation given. So with this equation, let's say t squared equals 12z minus 7. We have an equation. And as I mentioned prior to stepping into this example, an equation already displays a relationship, a connection, a rule that bounds the two variables together. No matter how you assign a value for one of the two variables, the other one have to come out accordingly. To satisfy this equation. So an equation itself is already a rule. We already had a rule. Okay, so in that way, now I'm going to call that part A. So we don't really have table. Table is for a different setting right here. But we still want to do the similar thing. I want to decide whether the equation, okay, defines or represents. So instead of table, it's just equation, but it's still, does that represent, or the more precise term is defines. Whether the equation defines, how about z as a function of t. Z as a function of t. All right, so there you go. I wrote down the instruction for that. Okay, so and now, similar to the earlier examples in this lesson, let's just write this in red ink right here. Z as a function of t, and I want that to be underlined. Very similar to the earlier two examples right there, where we had tables. So here, instead of table, we have an equation. And this equation, just like any of the table earlier, this equation involved two variables. So like what I explained earlier, seeing the two variables here, we can just take any one of these to be the input, and the other one will come out according to the rule here to be the output. But we want to step forward and decide, can that rule be decided as a function? Okay. So now let's look at the wording a little more closely right here. We want z as a function of t right here. So that means we want this one here to be the dependence variable. And this is of course the input. Okay, I mean the output. And on the other hand, we want this t to be the independent variable. And this is the input. That means we have to actively, first thing in line, assign different values for t, and then see how it comes out with that z right there. Okay, so now let's get to it. All right, so now on my other board space right here. So let's just remind ourselves that the equation here is a t squared times 12z minus 7. Okay, so even though we don't have table at started, but it's always a good idea to start out with table. And this time I'm going to draw a table as following. I want z to be the input. Okay, and t is to be the output. I think I'm having it opposite. In this problem, we want t, and so I want t to be the input, and the output is the z variable. Okay, so let's see how that can be done. So it's easy for the inputs part, which is randomly picked value, Okay, so now I'm going to pick -2 for t. Okay, so -2 for t, but how do we decide an output right here? So -2 in the role of this equation, it's -2 substituting for t, so -2 all squared, because it's t squared equals 12 times z minus 7. Okay, and so by doing that, this is going to be a positive 4, and I'm going to add 7 to the other side, so 12z equals 11. Okay, and so we can solve for z value right here being 11 over 12. So we have an output. 11 over 12. So here's the thing, right here, the problem, now unlike table, the problem with equation is that how far should we extend our table? How many times should we pick values? Should we continue doing this? Well, at least for the first shot that we chose right here, inputs -2 came out with one output. The calculation showed that. Showed that. But now try to understand my logic. Yes, ideally we are heading into that same way as we were doing with tables. We want to check because in order to make sure if this rule gives us a function, if this rule defines a function as a function, z as a function in terms of t, in order to decide that, we have to make sure for every input t, we come out with exactly one and only one output. We have done one input so far. We have only done one input so far. Yes, we came out with exactly one output, but how do we know that it's going to be the same, exactly one output for every other output? I mean, for every other input aside from -2. Because how many more inputs are we going to need to use in order to know that? That's the question. Well, we can try another one. -1. Okay. And now with the rule here, -1 all square equals 12z minus 7. Okay, that's a z. Okay, and so now once again, -1 all square is a 1 equals a 12z minus 7. I'm adding the 7 to the other side. That's leaving me 12z equals 8. Okay, because I'm adding, not subtracting. So that's 8. Okay, and then I'm dividing both sides by 12, so that leaves me a 2/3 equals z. So the answer for that is a 2/3. Okay, one input goes to one output. But the question now that I worry, right at the first moment I put down, how far should we check? How much further do we have to spend time checking? Because so far we checked 2 values, and in case you haven't noticed, now I point out for you, between -2 and -1, you can pick infinitely many other values between like a -1.5 between these, and you can use that in this equation and solve as well. There are a lot of values to solve. So how can we make sure that for each input there's only one output and only one output? How do we make sure that for each input there's exactly one and only one output? Okay, because we have tried 2, but now the work seems hopeless. Too much to try out there. Just to make sure one thing. Well, we can try another one, like a 0 for t. Okay. And we can try a positive 1. But notice in between these, in -1 and 0, there's a what? There's a -0.5. It's already between, there's a -0.25. Between, there's still many other values that we didn't reach to. Okay, let's try these. All right, so now in that way, well, when t equals 0, I have 0 squared equals 12z minus 7. And as I keep doing a routine on these values, you will start recognizing some generality and then save that thoughts for your next step right here. So I'm going to add 7 to the other side, and that's leaving me a 12z equals 7. And that now gives me 7 over 12 equals z. Okay, 7 over 12 equals z. Okay. So the output now is 712. So yes, one input going to one output, but I'm still feeling insecure. I'm still feeling threatened because there's still too many values that we didn't reach to. I spent so much time on the board right now in front of the camera only for checking 3 values. Yes, these 3 values are successful in a sense that each one of these guys is taken into exactly one and only one output. But what about the other guys? And as we finish with one guy with one input value, we find out there's another guy that we didn't check. And as we finish another guy, we found out there's still many other input value guys that we didn't check. Okay, let's quickly check for 1 right here. All right, so 1 square, the value for t, substitute it into the equation, and equals 12z minus 7. Okay, we check for that. Yes, that's 1. Okay, equals 12z minus 7. I'm going to add 7 to the other side. That's making it 8 equals 12z. Okay, and then now I'm dividing both sides by 12, so I'm looking at a 2/3 again equals z. So 1 comes to, and the calculation only gave us one value, 2/3. One input. Now it's different with that input, so we don't have to worry even though the 2 outputs here looks the same value. Okay, but that's not a worry because in the end if we focus just on that input, which is different with this input already. So this input goes in the end goes into exactly one and only one output. Okay, so I've tried 4 different input values, but now that's where the big worry comes out. How do we know if we have checked enough? Because the point, again, the point I got to emphasize, we need to check and make sure for each input there's exactly one and only one output. Okay, and so we have no way to secure that that part right there. We have no way to check if, for each input there's exactly one and only one output. So now we have to come up with a better solution. Otherwise, if we just keep trying out, table is not bad, okay, but table here reached to its limitation. We cannot list every value out there. We cannot reach to all values out there. Okay, so at least, now I've done a lot and erased a lot, but at least you start forming into a routine work right here. Okay, so here's how I'm seeing it. Now, this is the part where it needs to take algebra. It needs to take some elementary algebra, even though we're still doing algebra. But the more advanced one right before you ending up with the kind of algebra here you're learning is to equip you the deep enough understanding for calculus. That's why it's called a pre-calculus, or a lot of schools call that the college algebra. But now, back to the idea. See, for any arbitrary, for any general inputs, namely t, then in this equation, in this rule, this is the rule. This is the rule, okay? That's the rule right here. Okay, so for any t inputs, we want t squared to be equal to 12z minus 7. That's just straight out from the rule. So this t can take on different inputs. And so look at, you can always roll back at my video here and see how I was doing that. But what I've been doing so far throughout the 4 tries so far is that I can just, after I substitute in a value for t, so think about you substitute in a t for t. Okay, then what you do here, you can just add that 7 to the other side. So we're looking at t squared plus 7 to equals 12z. That's what I've done. That's a generality we concluded so that we can ensure for the rest of the other values we can just check like that. That's the whole point right there. Okay? Otherwise we're gonna keep, we're gonna get stuck with keep trying for every single input value, and that's impossible to be done. So now I'm gonna say arbitrarily arbitrarily, if we picked an input, or generally if we picked any input, if we set at any input t, what we can come out now is I'm going to add 7 to both sides of that equation, right there. So, ladies and gentlemen, at this point, I need you to bring back your skills that you must have learned in some elementary algebra course, that you, out of an equation, you solve for one variable in terms of the other one. And this is, again, my step right here for that. Okay, and it should be now familiar with what you have learned prior to entering this course. Okay, so now here, continuing solving further, and that's exactly like how I've been doing earlier, except earlier we had values so that we can formalize it, we can finalize into an actual number here, but that shouldn't be a big worry. Your mind is more mature now at this point. And now I'm going to divide both sides by 12, so that gives me z on one side, t squared plus 7 over 12 on the other side. Okay, and so now what have I found? So in case, now I'm comfortable enough to read the equation this way, but in case you're not, in a world of equation, you can write this same equation as saying z equals t squared plus 7 over 12. So now you can see that, hey, it's a good news here. It's a good news. For any inputs, you only have one expression like this, okay, and that lands you right into one output. Only one expression be represented by this z right here. And so this is the way how now, if you connect back to what you have learned after viewing my earlier video lessons about how I use equation notation to notate your function, then this is just fine. This is when you land right here. I mentioned earlier in that video lesson that we have only one single variable here, and equals an expression that involves the input variable. And this is where you can say yes, z can be regarded as a function of t, or t is the input and z is the output, because now we know that in this way, once we have expressed this, then for every input we give t, there's only one output value for z. This is the way to guarantee this. Okay, so once we have arrived with that, so the way how I see it, or rewriting your equation in a way where there's a, okay, one variable, or just say a single variable. Okay, a single variable, and then here an expression. Okay, an expression of the input and one variable for the function that we desire. That can guarantee that, hey, doing this, then for each input there will be, as soon as you can write your equation from beginning form into something like this, okay, then that is a way to guarantee that for each input you will come out with exactly one and only one output. Okay, and so in this way, now you have successfully earned that decision right there. You have successfully proven that decision that, hey, this function here, okay, so there's only one expression in terms of t that equals z. Okay, and so now I'm saying yes, z is a function, okay, of t. All right, so that's how we decided that. And so now I'm seeing again, see, and that's what I meant earlier, that there's only one expression. There's only one expression in terms of t, involving t. That's what the formal name in terms of t means. And all of that equals to one variable z. Okay, and so this form of the equation looks just like how I had that in my earlier lesson, in my earlier lecture, where I introduced the equation notation, of a function. That's how it is. We need only one, whoever variable that we want to be the function stays as a single variable on its own on one side, and on the opposite side, The rest is just whatever expression, but only involves the t right here. Only involve the input variable. And since we notice there's only one expression like that, of course I understand when you're learning through this video, you might be still a little worried about what does that mean by having only one expression. So does that mean there could be multiple expressions to equal this z? Wait for that problem to come. Okay, and as a matter of fact, it exists right here in this example of yours. We will come to that. But right now, I only see right in front of your eyes right here, one expression equals, and one expression that involved the tentative input variable. I call it tentative input because we wanted that to be the input. And there's only one expression involving that input. And then all of that equals to the single variable where we tentatively wanted that to be the z, to be the output. Then that's now enough for us to make a conclusion. The conclusion that that z is a function of t, of the t variable. All right, so now once we've settled and start realizing the idea, it took me some time to explain this because I want the student now, of course, the whole reason of delivering an online a video lesson like this, because anyone learning from this lesson is taking the math course online. And so, of course, we're lacking that face-to-face instruction right there. And so that's why I have to prepare all kinds of details in case somebody is missing, somebody missed this information, somebody missed other information. Okay, so same equation. Okay, same equation, same example 3. Let's call that part B right here. All right. Let's now part B. I want to decide whether the equation can define t, okay, as a function of z. All right, can t be a function of z? As I said earlier, and as I have explained often enough, prior to stepping into this example, then either you're having a table or you're having an equation like this that involves two variables. Then any one of them can be picked as the input. And then the other one will come out according to the rule to be the output. So here we want that t to take the rule as the output. Or, yes, this is the dependent variable. Whereas I want the z to be the input, where it's playing in the role of the independent variable. Okay? So just like that, let me now switch over to the other board. I'm going to quickly erase the board. And we're going to do the very similar thing. But hopefully I can start coming up with steps already. So the rule is still here. The rule is still here. We will construct a table. One for t, the table with two columns, one for t and one for z. Okay. And so in this case, we want these two variables to switch roles. So z is the input and t is the output. But the rule is here. I still highlight that with the brackets right there. This is the rule. So we already had a rule. We know we had a rule that relates our inputs with the outputs. Okay, the rule that connects the inputs and the outputs together. No matter what you choose for the inputs, the output has to come out accordingly. Okay, or in this setting right here, the inputs and the outputs together as two values must satisfy that equation. Okay, and so that's the idea. But now, again, in this case, we want z to be the input, and we want t to be the output. So let's see how we can get it done. All right. So I'm looking at, how about 0 for z? Okay, 0 for z. And so here we're looking at t squared equals 12 times 0 minus 7. Because now z is the one that's given an input value. So we're going to substitute that into the equation. And we want to find out what value of t will satisfy this. So that's a 0 and that's a -7. So -7 times t squared. Okay? And so now we're going to take the square root of both sides. And the square root of both sides giving me a positive. Taking the square roots both sides of any equation will always give us two different expressions. One of them is a positive square root of -7. The other one is a negative square root of -7, in the way how it is right now. Okay? But so now here, wait a minute. This is undefined. This is undefined because square root, at least we are still, I mean, for anyone learning in pre-calculus, the earlier part, the beginning part of pre-calculus, we are completely in the world of real numbers. So in our world of real numbers, we cannot take square root of -7. So we can't even have plus and minus square root of -7, because right before we are worrying about the plus and minus square root right here, then we can't even take the square root of a negative number. So here, giving an input 0, we have an undefined here. Okay, then let's leave it there, but let's choose other values. So we just know that we won't have an output correspondingly for this. Okay, and then in later lesson, in other lesson, I will talk about the for any rule, there's a certain zones, there's a certain the limitations to the inputs right there. So what inputs we should choose to give a successful output. Otherwise, like this, we have an undefined. We don't know how to calculate the outputs here. Okay, so let's now try with how about z equals 1. Okay, now if z equals 1, we have t squared equals 12 times 1 minus 7. Okay, 12 times 1 minus 7. This means t squared equals 5, because 12 times 1 is 12 minus 7, that's 5. Okay, and now we have a t squared equals 5. So solving for the value of t, we take the square root of both sides, but now don't forget, again, I've done that in the earlier demonstration, and now I'm doing that here again. Plus and minus square root of 5. That's the only way, because anytime we are finding a value for a value that's being a square like this, there are two roots, positive and negative roots. Okay, but this is the scary part right here. This is the output. It comes out with two values. It comes out with two values. The same inputs 1. The same inputs 1. One of the output is a positive square root of 5. The same input 1, but we realize that it could also be a square root of 5. How scary is that? Okay, because think about it. This just now is a violation for being a function. We have a rule that relates inputs with outputs, but this rule here just now we ran immediately into that case where it points out it fails that fact that for every input there's exactly one and only one output. This fails right there. This fails right there, immediately right there. Okay, because one input. But so when that's the reason why it fails, because how do we know when we work with that? How do we know when it runs into a positive square root of 5 and when that same inputs will give us an output negative square root of 5? Think about if this function of yours, if this was a function and you are working with that as a machine, then how do we know when your machines will behave in the way you want? Okay, because sometimes it gives a positive square root of 5, sometimes the same input it gives a negative square root of 5. That's the scary part. Okay, and so we have a rule, we have inputs, we have outputs, but this rule here fails to give exactly one output for each input right here. That's the failure of this part right here. Okay, and so now as a generality, you can see the following. And let's try again. I mean, even though it already fails, but let's look at another one to also draw out a conclusion right here. Because in other case, now we are lucky that this example puts you in a failure case immediately, so that you can make your decision, but some other time it doesn't. Some other time the failing part doesn't come out immediately yet. So we need to come up with a solution that's more generality. So how about when it's 1, we're looking at positive or negative square root of 5. 2 different outputs for now, notice. But I still have my reason to move on because, as I said, this example, we're lucky that we run immediately into the failing point. But in some other ones, it keep working out until some much later trial. Okay, so let's keep trying. If z equals 2 as an input, okay, if z equals 2 as an input, then t squared equals 12 times 2 minus 7. Okay, and that's making it 24 minus 7, which is t squared equals 17. Okay, so that means t is, again, taking square roots, plus and minus square root of 17. Now, needless to say, square root of 5 or square root of 17, these are all defined value. It's just not a nice looking value, but at least they're all defined, meaning we can have a value for that. But in the end, it must be, it will be a very ugly looking decimals, but it's a real existing value, defined. That's what it means. Okay, but again, we run into that same crisis there. 1 input gives us 2 outputs. There can possibly be a positive square root of 17 and possibly a negative square root of 17. So 2 fails already. But now after 2 fails, and including the try that I've done, including the attempt I've done when it came out with an undefined here, let's come up with something. It seems like, as a generality, because like I said, in some other time when you're working with an equation, the scary part is, you see, even though between 1 and 2 right here, I already left out a lot of values in between I didn't check for. I checked these 2, they fail, well, we're good to go. But what if I chose other values that didn't fail yet? And how far do we know to choose before we run into a failure? Okay, how many values do we have to choose before we run into a failure? Nobody knows that. Okay, nobody can guarantee that. So here's how I see it. If t squared equals, suppose z is substituted by an arbitrary value, 12z minus 7. Some z substituted for z. Okay, suppose z is at some arbitrary value. Then I can see that finding the value for t, I've been doing up to 3 tries so far. And the common thing here is we can just take the square root on both sides of that equation. And that's the square root of 12z minus 7. Think about if z was already assigned with a value. Think about if z was already at an arbitrary value for them. Okay? Then taking the square root of that entire expression gives me, so now here's what we're ending up with. So now it makes it clear here. We can't run away from it. We can't hide away from this truth here. No matter what arbitrary value z is at for the input, the outputs for t, for t variable, we will always run into 2 outputs. How do I know that? Because there are 2 expressions. This really means that we have 2 expressions. On one hand, t equals a positive square root of 12z minus 7. And on the other hand, we can determine t by running a negative square root of 12z minus 7. That's where the problem is. One input, but we come up with 2 different outputs determined by 2 different formulas here. Okay? And this is the part where making this rule fails to be a function. Okay, so now I'm going to have to make that conclusion on my other board. Okay, so I'm just going to use a common language here. So due to 2 expressions, plus and minus 12, there are many ways of interpreting it, but same logic. 2 expressions. One of them is plus, the other one is minus, square root of all that, 12z minus 7. both equal t. Okay, so this is we just say, I was about to say fail to become, but here we can just say nope. T is not, okay, t is not a function of the z variable. That's how it's decided. That's how we can making our conclusion. That's how we're making our conclusion. Okay, and so you see, so this way of reasoning right here, if you are doing, at least for me being my student right here, anyone being my student, if you're doing this kind of problem right here, all you need to do is show your steps to the point where it shows, you know, two expressions equals to one variable. That's enough to say nope, it's not a function of. Or in the earlier part, show your steps where it comes to exactly one expression to equal a single variable. That's, you say yes, that's your, you have a function. But I don't need anyone to write down this real detailed explanation here, because this is the part where it's just the logical process in your mind only. And at least for my students, you don't have to write this line down right there if you're doing your written work, when you're deciding whether an equation can be a function or not. Okay, and furthermore, in these advanced days, in these days where we live with a lot of technologies around us, most likely when you are working with a homework assignment or something like that, these kind of problems remain as those where you can quickly decide. So nobody is asking for steps as well. You just know these steps on your own, and then you just simply decide as a quick response answer, is this a yes or a no? Okay, but now to get you more experience, let's head out into example 2 right there. Okay, let's head out into example 2. So this is the end of example 1. You have already learned enough. And my point here is that now, see, aside from having a table representation, you can have an equation that points out some kind of rules between input and output. But will that rule be a function or not? It still depends on a lot of work to decide. And you have seen that through example 3 here. Okay, but let's look at a further example. And very similar. I just intend to bring up this example to get you more algebra experience like that. To get you more algebra experience. So and that's why I can legally retain a lot of writing from the earlier example. Let's now call that example 4. Okay, and now we are given the following equation. How about s squared minus 18s, okay, minus 2w plus 28 to equal 0. It's an equation. Okay, it has two variables involved. There's the s variable and there's the w variable. Okay, and part A, let's decide whether the equation defines w as a function of s. Okay, and so now I no longer need to write that the w and s in red ink, because you already got a good hang of that. Anyone viewing this video has already had a good hang of that. So you know where it's focused your attention right there. Okay, and now once you've already had some good experience from example 3, allow me to just show the shortened steps, but still legal, because in the end, this kind of problems in the end is meant to be just a quick decided one, a quick decision one, where not too many professors out there is asking for formal written steps to defend your answer. So you just say yes or no. But before you can arrive to a yes being a function in terms of the other one, or saying no, not a function of the other one, there are a lot of steps in the thought process where you have to write it out on scratch work somewhere. Okay, so now allow me to show all of that in a shortened step, so that we can eventually come to the final answer here. All right, so let's head out to the other space of the board right there. And with this example 4, once you see this step right here, you can think about, after you grow a little more mature in doing this, then even example 3, I could have done that with the shortened step as well. But it's just earlier I had to show the thinking process of that. Okay, but now this is now just the formalized legal thought process right here. Your equation, as a rule, it's a rule. S squared minus 18s minus 2w plus 28 equals 0. It's an equation, two variables involved, and I want this w here is to be the function. That's what it said in the problem. I want this w here to be the dependent one. Okay, or it's the output. And I want all of these s's right here, that is to be the independent one. Okay, this is the inputs. We definitely don't want to bring up tables anymore and trying out, because trying out throughout table is just a very lengthy but ineffective solution. We will never reach to what we need to decide. And so now let's get straight into the point right there without beating around the bush. You have an equation and you want to decide whether or not you can express w as a function dependent on the s variable. So here's how you're doing it. Solve. The main way is solve for w, okay, in terms of s. That's what you need to do first. That's what you need to do first. And this is where you need to bring back your skills that you have already learned prior to entering this course right there. You have an equation that involves two or more variables, and you pick to one variable and solve for that particular variable. Here we are asked to pick w and solve for w in terms of s. Okay, so now that means our equation s squared minus 18s minus 2w plus 28 equals 0. In the world of any equation, you can just simply subtract both sides of the equation by an expression. We've known all that. Or add both the same expression to both sides of an equation. So here it was already a subtraction, so I'm going to add 2w from both sides. And now I'm ending up with s squared minus 18s plus 28 to equal 0. The goal is to bring the desired variable to one side on its own as a single variable and see if we can successfully rearrange the whole equation in terms of s on the opposite side. That's the goal. Hear my goal verbally. Okay, so you can always roll back the video and hear what that goal was. The goal is, again, to bring that desired variable to one side as a single variable. And then the rest, the opposite side, is an expression only in terms of s. Okay, I said it twice. So now I shouldn't have that 0 here. This is a 2w. Okay, so now that's what I did. So now I'm slowly, at least up to this point, I've brought all the w terms to one side. Left hand side or right hand side is pretty much your choice right there for that. So 2w equals all that here, and this is already in terms of s right here, an expression that only involves s. We're slowly getting there to our goal right there. Okay, but this 2w is not quite satisfying the expression because I want just one single variable. Coefficient 2 is not good yet. It's not good enough yet. So I'm going to divide both sides by 2. Okay, I'm going to divide both sides by 2. All right, and so now I'm looking at dividing both sides by 2. I'm looking at w equals 1/2 s squared, and of course you are required to know how to operate with these basic operations right here. Minus 9s plus 14 equals w. W equal an expression 1/2 s squared minus 9s plus 14. That is a variable, one single variable equals an expression in terms of the other variable. That's how we rearranged this starting equation. But now, hey, look on the bright side. We only have one expression in terms of S equals one single variable of W. So this is where now I can put a check mark right here. This equation defines okay, W as a function of S. All right, so now as long as we reach to that, we don't need to put it in any other beating around the bush argument like that. Just as soon as we reach to that, okay, successfully expressed W as one expression of S. Now you can say, yes, okay, W is a function of S. That's what it is. That's what it is. All right, and so let's look at some more problems like that. Let's look at part B of the examples like that. So again, as I said earlier, an equation is just an equation. It's a rule. It's relating two variables. So any one of these two can be the input and the other one can be the output. So this time let's choose S to be the output and W to be the input. And there we go. We come to part B. We want to decide if this equation defines S as a function of W. Okay? Now, it takes me a lot of time to go through the example because I purposely chose a harder example so that it has a lot of details in case outside of this video, when you run into the challenging assignment, all of that details are in here in any of these problems right here throughout the examples. Okay, and so all right, so now on this board right here, the starting equation was S squared minus 18S minus 2W plus 28 equals 0. This time we want a very similar action, very similar work. We want to, from that equation, our goal is to express S as a function of W. Okay, we want S to be the dependent one and W is the independent one. So we need to solve here. We need to solve for S. Okay, because it makes sense. We want to solve for S because S is the dependent one. So once we solve for S, having S stands by itself and equals some expression of W, then the expression in terms of W will be the one that decides the final value for S. That's why it's making it perfectly consistent with the fact that S is the dependent variable. Okay, so that's basically what we want here. We want one single S variable equals an expression. And as long as we reach to exactly one expression, exactly one expression that equals S, we say it's a yes, it's a function. Otherwise, if it's two expressions, and it all depends on your algebra skills that you've learned from your previous course. In terms of solving, from an equation, we're solving for one variable as an expression involving the other variables. Okay. So now from this equation, this is how I see it. I want to solve for S. So let's start out by isolating. All of the S terms on one side right here. Actually, here's the observation. Our equation, see, what I see here is a quadratic. This is quadratic. Okay, see, quadratic term, linear term of a quadratic, and all that here. Even though it has that W, it's being a variable. But in the end, if we focus on S as the main variable of a quadratic, then all that here is just a constant. Okay, so now here's how I'm working on that. I'm going to use a quadratic formula. Okay, A equals 1, B equals minus 18, okay, and C equals minus 2W plus 28. The quadratic formula is what I'm about to use right here. You can see A S squared plus BS plus C like that. Okay, so now I'm going to need more space, so I'll have to erase this. quadratic formula says S equals minus b plus and minus square root of b squared minus 4ac over 2a. And just now I pinpoint what a is in this equation and what's the rho of b in this equation and what's the rho of c in this equation. So now we are ready. Okay, so that means S equals minus, b is a negative 18, okay, plus and minus, this is square root, okay, b squared is a minus 18 all square, okay, minus 4 times a, which is 1, times c, which is all that minus 2w plus 28. All right, and all of that there is divided by 2a, which is 2. Okay, and so now with this expression, let's simplify it down. And so all of those skills you've learned about simplifying expressions, you got to bring it all in here. So simplifying this, I'm looking at positive 18 plus and minus square root now, and then minus 18 but all square. Okay, that is a 244. Actually, 324. All right. And then now minus 4 times 1 and multiply with all that. So minus 4 times a negative 2w plus 28. I decided to go in a little bit of a slower pace instead of rushing. That's how I get that. Okay. And then gladly we have among these two, and it's all just how we simplify the expression right here, but 324 has a common factor of 4, and that has a common factor of 4 as well. We can pull it outside of the square root right here. Okay, so let me now erase this work right here because I need more space. Okay, so continuing to solve that, we're looking at continuing those steps like that. I'm looking at 18 plus and minus. Now factoring out the 4, it becomes 2 times the square root. And now it's 81 minus negative 2w plus 28. Okay, and all over 2. But now that is helping it to cancel out the 2 over here. So in my next step, the expression will become shorter. But notice, since the earlier steps, we've been stuck with that plus and minus. And it will come to that final decision point right there. So 18 cancel with 2 gives me a 9. 2 cancel with 2, so now it's just plus and minus one single square root, no more the denominator. So 81 now minus negative 2w, and so it's going to be a plus 2w minus 28. Okay, and so that comes to S equals 9 plus and minus square root of 2w plus 53. All right, so 2w plus 53. And so now this is where we can start making our decision. And now I can erase all of this. All right, so that means S here on one hand equals 9 plus 2w plus 23. And at the same time, S equals minus 9 minus the square root of 2w plus 53. And so now I've just made it apparent, made it very clear that when we're trying to solve for S as an expression in terms of w, see, we got expressions in terms of W. On the opposite side, one single S, one single S. But the problem is here, we have two expressions in terms of W, both equal S. And that's where it violates the rule for being a function. We cannot have one input that goes into two separate outputs because we had two different expressions like this. Okay, so now as soon as you can point out that you can pinpoint that one single variable that's tentatively to be the function to equal two expressions involving the input variable tentatively, then you can now say no. Okay, S is not or cannot be a function of W. Of W. All right, and that's how it works, and that's how the formal steps are performed or carried out throughout these kind of problems. But in this entire lesson right here, it could have been a lengthy one already, but you have to learn how to decide whether a rule. What we have here is a rule either given as a table, or a rule just now in example 3 and 4 given as an equation. And any of those rules, yes, they relate between input and output, but any of those rules, okay, can be function or can be not function. That's how we have to specifically learn that skill in this lesson, that how we can decide if any of those rules can be a function or not. Okay.